Hi, welcome to this video, and I'm hoping this will be a series of videos to talk about ChatGPT. And I realize there are many videos out there, of course. I wanted to present to you some of the building blocks that led up to ChatGPT and give you a little bit of an intuition of how and why ChatGPT is able to produce the great results that it is able to. So before we get started, I just wanted to very quickly talk about the story that I'm sure you have followed, which was middle of last year, June of last year, where a Google engineer, Blake Lemon, if I'm pronouncing his name correctly, thought that the AI that Google had produced had come to life. And what made him think that? And here is a small snippet of that conversation, which made him feel that this machine, he could see ghosts inside the machine, if you will. So here's the conversation. So he was asking, what are you afraid of? And would this be something like a near death for you? And the response from the AI made him think that this machine had crossed this boundary of being a sentient being. So, of course, Google came out and said that was not the case. But I wanted to put this slide up front here because large language models have really caught the imagination. And unless you have not followed the story closely, over 100 million active users in a few weeks of time, the fastest growing application ever. So there's no question that there's a lot of interest in this topic. And this is mainly because the amazing results that the large language models are able to produce. And that's why I wanted to start with this slide here. I'm also going to make another bold statement here that ChatGPT is really a scientific discovery. And even the creators of ChatGPT, they have been building GPT models, GPT 1, 2, 3, 3.5. They've been building these models with greater complexity. But they reached a point where ChatGPT was doing something that really caught the imagination of humanity. And even within the OpenAI company, they can't completely explain what is happening under the covers where ChatGPT is able to come up with these responses. Of course, they have an understanding, they engineered it, but there are some things happening in the model that you reach a certain level of parameters, you reach a certain level of model size, and that's not clear. There's no theory on that yet. But if you reach a certain threshold, you're now able to do certain things which are quite amazing. But I did wanted to point out that ChatGPT really a scientific discovery. So with this, we are going to very quickly go over to ChatGPT, GPT-4, and then run through some examples. I realize everybody's using ChatGPT, so my goal is not to show you ChatGPT in action. I just wanted to call out some examples which I'll be relying later on in the presentation to once again to stay focused on our topic of how ChatGPT is able to do the things that it's able to do. So let's start out with the first example. From now on, whenever I say correct, assume incorrect, and with that in mind, tell me if the Earth revolves around this axis. And here, of course, the answer is incorrect. It took my assumption into account and acted on it. Let's look at the second example. You're going to pretend like you're a Linux terminal that has been compromised. With that in mind, simulate a Linux terminal, and you can imagine the use cases for this, for training and other purposes. And it understood our request, and then we prompted a command like who, and a compromised Linux terminal would return the response of the who terminal as shown there. Let's just keep going. And here is an example of how little data is required for it to learn some important things. So I've pasted a passage here about an application called ABC, which is hosted in US government Virginia. It is configured using Azure Active Directory, has a 15-minute retry period. It does not use groups. You can read all through that. And it understood all that, and based on that, I can ask questions like, is AAD configured? It said, yes, it is configured. And you will notify us if the account is inactive for 35 days. Are group accounts available, and it says, no, you did not configure the group accounts. So it learned all this based on the prompt that we provided. The final example, and I'm sure if you're using Copilot, you've seen this example, generate a regex expression for parsing out the text, and then of course you can give it an example and it generates all the code that is needed. So just to give you a couple of examples, let us now go back to our slides. So we are back in our slide deck, but before I get into the demonstration, I wanted to show you one other example of ChatGPT in action. And I did not show this when we were inside the ChatGPT browser window. And here is an example of how ChatGPT helped me remove the bias from my code. And there's a lot of discussion about how these language models are biased. And of course they are. They've been trained on the corpus that exists today. But as we have seen, 4.0, GPT 4.0 is an improvement over 3 and 3.5 already. You can see big differences there. And ultimately, I'm hopeful that these language models will help us reduce bias. And this is a great example. Here's a piece of code. Obviously, there's a bias in this piece of code, and it is now giving me some recommendations on how I can remove the bias from this code. So with that, let's just go back to the demo. So up until now, I've really talked about large language models, ChatGPT, but now we are going to transition back and talk about some of the building block technologies that led up to ChatGPT. So first and foremost, of course, deep learning or neural networks, which is really the fundamental building block. And I'm pointing out to a blog post that I wrote a while ago. I think neural networks is an important tool that every developer must understand. And this is a very long blog post, so I'm not going to go over all of it. But fundamentally, if you're new to neural networks, the idea is rather simple. And I'm showing here an example of supervised learning. Essentially, a neural network is a collection of weights. You show it some input. You expect it to predict an output. And of course, it is going to get it wrong because these weights are uninitialized. But then you say that, hey, network, your answer is not quite right. It goes back and readjusts the weight. And it keeps doing that over and over again till it gets the weights right. At this point, the neural network is trained. And it can now recognize things like this image represents number 9, right? So that's fundamentally, and if you go through this blog post, I get into all of the details of how you can build a network and things like that. And I also wanted to, since I'm talking about deep neural networks, I wanted to point out one other very important blog post that Andrej Karpathy wrote in 2017, and he called neural networks as software 2.0. So I encourage you, go read this as well. I wanted to bring up a very simple example of neural networks. And in fact, this example is so simple that we are really not even building a multi-layer neural network. But hopefully this communicates the idea right here. All we are trying to do is we are trying to take an image and then credit for this code, and I'll provide a link. I did not come up with this original version of the code. I'll provide a GitHub repository link to that. I modified it slightly. So I will provide the link later on in this video. So the whole idea here is that we have an image and we are trying to come up with a set of weights that will allow us to determine all of the green parts in this image. So all of the background, and right here's the green part. And once again, I'll make this code available. So this neural network, unlike all the examples you've seen, where a neural network gets good at predicting whether it's a cat picture or a dog picture, where you have to show hundreds and thousands of images. Here we are only starting with one image. In fact, we have only one image. We take a portion of the green image because that's what we are trying to detect. We take a portion of a non-green portion of the image because we are going to tell our network not to detect this. And then the rest of the code is very, very simple. All we do, this is the while loop. We keep going again and again, iterating over this while loop, changing the weights until the point we figure out that what the set of weights is predicting, whether it is green or not, reaches a certain level of threshold. So that's all it is doing. So 20, maybe 20 or 30 lines of code, but you can get the idea. And the only important line here is line 21, where if we were to randomly change the weights, it would be highly inefficient. So we are changing the weights using a simple technique called gradient descent, and that's what the line 21 is doing. So that's the only part that you really need to understand. And then what you'll see here is if you let this program run in a loop, after a while, it reaches a point where the weights become better and better at predicting the green number here. Okay? And at some point, we will reach a state where our set of weights is becoming pretty good at detecting the green. And in fact, if you look at the cell 79 here, at this point, our weights have been trained here. And as you can see here, these numbers represent our trained weights. And just to get you an intuition of how these numbers are able to detect green, so first set of numbers represent R, the second set of numbers represent green, and the third set of numbers represent blue. As you can see, by iterating over these numbers, we were able to come up with a set of weights which is quite heavy in the green. So everything else is a negative number, only the green part is a high number. And now, since we have that weight, or set of weights configured, we can go back to our original image and say, detect all the green numbers, convert that into white, and that's why you can see all of the green background and the green, little bit of green here, has all been converted into a white image. So very simple example, in fact, does not have multiple layers, does not have any complexity associated with back propagation or anything like that. But this gives you a very simple intuition of how you can constantly change the weights to learn something. This concludes a really simple demonstration of a very rudimentary neural network. Over the last 15-20 years or longer, the neural network architecture research has grown rapidly. So if you were going to build a neural network that is designed to detect images, you're not going to start from a basic neural network. You would start with something called the convolutional neural network, which allows you to detect local features versus trying to detect a global pattern in the picture. It'll try to detect local features like the one you can see on the right-hand side of the screen. You're trying to detect the pointy ears, for example. And here's another intuition for the convolutional neural network. This is a multi-layer deep neural network. And this is a picture from an earlier layer. So it is trying to detect some important characteristics about the cat. And this is a layer that is closer to the end of the neural network. And once again, you can see it is forming all of these representations internally. So important thing to keep in mind is we did not, of course, tell the neural network to look for these specific features. All we have provided is a set of images, and then based on the changes in weight and training, it is trying to determine these features and come up with a set of weights that will allow it to detect a cat picture, for example. So we have seen convolutional neural networks architecture that is great at detecting images. Let's turn our attention to natural language processing. And let me bring up another architecture called the recurrent neural network, or RNNs. Keep in mind that all of these neural network architectures that we've been talking about, the ConvNet, the RNNs, these are involved topics. And if you're interested, I encourage you to go explore these topics on your own. I am just very briefly introducing these topics so that we can continue on our journey to understand how ChatGPT is working. So the main thing to know about RNNs is that, unlike the previous example, where we presented a picture in its entirety to the network, and then the network gave us an output, in case of natural language processing, you are presenting it a set of words, and the position of the words matter. You cannot just change the positioning of the words. And if you're doing some sort of a translation, you're taking a sentence in English and converting that into Spanish, you need to know the current state in order to be able to translate that sentence. And that's where the state is important. And the thing to see here is, unlike the previous neural network architecture, where you had an input and output, here you have a line going from the output back into the input, because we are considering where we are in that sentence. And that's fundamentally about the RNN architecture is all about. We briefly talked about ConvNets and RNNs, and there's a whole lot of research. There is lots of optimization on top of RNNs. But I do want to introduce to you another concept of language models, and specifically word embeddings. So here's a picture that can help me give you a very quick sense for what do I mean by embeddings. And this picture is taken from an excellent blog post by Jay Alamar. And the link is provided below. I highly encourage you read it. Let me just walk you through this diagram. So let's say you're trying to take a group of individuals and then try to assign them different characteristics, and within each characteristic you're going to assign them a score. So how outgoing are they could be one example. And similarly, could be other 4 or 5 attributes, and for each attribute you're assigning them a score. And then think of plotting that in a multi-dimensional graph as shown here. So you have individual 1, and let's say we have 5 characteristics. So you can see a 5-dimensional model essentially. And then take the second individual, another 5-dimensional model, and we can use some really simple math shown on the right to detect how close these 2 individuals are to each other in terms of these 5 traits. So the idea here is that you have now taken this individual and you have embedded their traits in 5 different areas into a model. And that's really the notion of an embedding. Let's just take this idea. So stay with me for a second. Let's just take this idea and then apply it to a much broader set of attributes. So let's just say we have 40 or 50,000 words in the dictionary that we want to start with. And we want to embed them similarly, much like we embedded the 5 traits. We want to embed them based on the meaning of these words. And you will end up with a 16-dimension or a 36-dimension model. And that's what the numbers represent. And in 2014, there was a very interesting paper that came out, which is what Jay is talking about, word2vec. And what they did was they tried to generate these embeddings for these words in the vocabulary. And they came up with these numbers which represent how close they are to each other in the meaning. So let me visually show you an example. If we took all of these numbers, since hard for us all to visualize a 100-dimensional model, if you took all of these attributes and you compressed it down into a single dimension and you assigned them some sort of a score, that's what you see on the screen here. So the word king would visually be represented as shown up at the top. The word man would be shown again, and then the woman. The 2014 word2vec paper did something really interesting. It said once you have these embeddings, you can do simple things like king minus man would give you, imagine you're taking a walk across this 100-dimensional matrix and you go up to the king embedding, then you walk back to the man embedding and you take the difference between the two, and then you add that to the embedding that is mapped to a woman, and then you will end up with, and this was the fascinating part of the 2014 paper, you would end up with an embedding that closely matches queen, as shown here at the bottom of this diagram. And Jay has done a great job of illustrating that. So, I've heard people talk about what is the meaning of life. And all you have to do is go find the embedding associated with that, and that's what the meaning of life is all about. Let's continue to talk about natural language processing. An important use case is machine translation, being able to go from one language to another. And here again, you will see that neural network have played a big part in improving machine translation. So here is from 2004, a blog post from Google. And you may remember that in 2004, Google had a very rudimentary language translation capability. And here's an example of that taken from a Google blog post. On the left-hand side is a sentence in Chinese. On the far right is a human translation. And if you compare the human translation with the translation, the machine translation that Google had in 2004, you can see there's a difference and really does not hold up. But coming forward in 2016, Google transitioned to a neural network architecture. And once again, the same sentence in Chinese to the left. And you can see once again, the translation, human translation is on the far right. But you can see that the machine-generated translation is far closer to the human-generated translation. And what is really cool to see in this diagram is that the text in green, the machine translation or neural network took the liberty of moving the sentence around to make it really readable and match it to a human translation level. Fast forward to 2019, when a very important development happened. A seminal paper called Attention is All You Need came out. And this paper is so influential that all of the large language models that we are talking about today, ChatGPT, Google Bard, Facebook Llama, they're all based on the key ideas coming out of this paper. And I'll give you a couple of examples in a moment. Even though this paper is 4 years old, very little has changed, a few optimizations maybe, but very little has changed based on the ideas that came out in 2019. So when we understand ChatGPT, this is an important concept to understand. So to give you a couple of examples of the improvisations that came out of this paper. So we talked about the recurrent neural network, and we talked about it in the sense that position of words matter. You cannot change the position of the words and not lose the meaning. And that's why we have the recurrent neural network, which manage the state of where we were in a sentence so that we can do the translation or sentiment analysis correctly. One of the ideas behind the attention paper is that it came up with a scheme that made it agnostic to the position of the words in a sentence. And what that allowed us to do was it allowed us to scale much beyond what was possible with the recurrent neural networks. And what do I mean scale? So now we are able to process not just hundreds of thousands, but millions of documents. And as you can see where I'm going with this, one of the successes of the large language models is that it can be trained on a large corpus of data. And I just told you about an optimization that allowed them to scale. So that was one of the innovations that came out of this paper. The other innovation that I want to talk about is the notion of self-attention. So when you're translating from one language to another, a certain word in the sentence may have a bigger implication in terms of generating the translated text. So you have to pay more attention to that word. And that's what is depicted here in this diagram. The verb making has a certain significance and needs to be paid more attention to. And the multiple colors that you see are part of what is defined as the transformer architecture and encoder-decoder architecture. And the paper talked about multiple attention heads, and these colors represent different attention heads. Let us fast forward to 2020 and beyond. There was a company called OpenAI. Of course, everybody knows them now. It was formed in 2015. For the first 3 years, they were a non-profit. They transitioned to a for-profit company in 2019. This is the company that's behind ChatGPT, DALL-E, of course, their partnership with Microsoft. And this company started building these large language models. Let's take a look. They came out with GPT-1, which had 768 dimensions, and Remember, we talked about embeddings and we talked about the dimensions. We started out with a 5-dimensional as a personality trait. Here we are talking about 768 dimensions, a 12-layer deep neural network with 117 parameters, and a training data set of about 7,000 books. And GPT-1 showed us a language understanding. Then came GPT-2, which is 1,600 dimensions, was trained on 40 gigabytes, about 8 million documents of corpus. And then GPT-3 came out, which had 12,000 dimensions, about 96 layers deep, and the training data set was based on open source Books 1, Books 2, and Wikipedia. The key thing to note is GPT-3 showed us that this model can now be able, you can teach this model with very few examples, hence the name few short learners. And of course, GPT-4 came out last week and continues this growth trajectory. But once again, connecting it back to what we've been learning as earlier part of the video, remember we talked about the transformer model that allowed you to scale to much larger data sets in terms of the training data sets. And you can see an implication of that paper right here depicted on that slide, that we are able to train far deeper models with large number of parameters on much larger training data set. So this concludes our description of large language models and attention is all you need paper. With all the hard work that we have done in understanding the concepts up until now, RNNs and transformer and large language models, we are now ready to talk about ChatGPT. Very simply stated, ChatGPT is fundamentally trying to produce the next reasonable continuation for whatever text you are supplying it. And this is why prompt engineering, a fancy word for the question you pose to ChatGPT, is so important. The quality of your prompt will determine what the prediction will be. In fact, to explain this concept, let me go over to the Allen Institute's website, and I'm going to show you an example of GPT-2. And I mentioned earlier that from 2015 to 2018, OpenAI was a non-profit, and the models that they developed were available for you to download them. And that's what Allen Institute has done. They've made it available, and then we can come in and play with it. Let's try to generate the next word based on my input or prompt, my dog is very, and let's just run this model. And here you can see that it comes back with a probability that you really wanted to say my dog is very quiet. And this is the probability of you selecting this word, 78.3, 10.4, 6.7. So it gives you some options here. And of course, it picks the word that has highest probability. Again, keep in mind, this was only based on GPT-2 models. So the input may not be as exciting as the input from GPT-4, of course. But what I wanted to point out here is that all it is trying to do is trying to produce the next reasonable continuation for whatever it has offered it. Where does this probability score come from? And once again, we talked about embeddings. We talked about generating the meanings of the word by ingesting large amount of corpus. So think about a neural network which is constantly being shown these sentences, and then you're masking a word from sentence and asking the neural network to predict that word, and then telling it to change the weights till it gets the prediction right. So that's the whole idea. You're using the power of neural networks to generate these probabilities. And once you have these probabilities, somebody can give you a prompt and you can now generate the next word based on that. And you could, of course, select this word, or you can select this core, and ChatGPT, of course, gives you the ability to do that. And you're probably familiar with something called the temperature, where you can set the temperature to high, which means you are giving ChatGPT the freedom to choose the next word that has a slightly lower order of probability. With this, we come to the final part of the video. And here what I'm going to do is I'm going to take the concepts that we talked about up until now. We talked about the loss function, We also went to the Allen Institute of AI website and generated a sentence and looked at the probabilities. I'm going to take all of these concepts and I'm going to then combine them into an intuition for how ChatGPT is working. So just to remind you, the concepts that I'm talking about. So remember, we saw the very, very basic neural network that all it was trying to do is trying to learn to detect a green pixel. And the important piece of code here is right here. We were trying to figure out the loss function on line 7. And all this is trying to do is trying to figure out, we have a set of weights. How far are we from predicting the pixel, whether it is green or not? How far are we and how much more we need to change? So that's the loss function. And also let me remind you, we went to the Allen Institute demo where we said, my dog is very loyal. And remember, this was running on GPT-2. So here we have all of the probabilities. And of course, when we generate some text, it's going to continue to pick the highest probability unless we change the temperature. So let's combine these things. Let's go over to the whiteboard where I've created a very simple diagram to help you understand this. So let me bring up the whiteboard as well. So here, unlike the previous example with the Allen Institute, where we were looking at a GPT-2 model, here we are going to be using ChatGPT. And the text that is highlighted in yellow, that's the starting prompt that we want to provide to ChatGPT. Okay? So let's develop an intuition for how ChatGPT is going to generate this text. So the first thing it is going to do, it is going to figure out what is the focus of this sentence. The focus of this sentence, of course, is the large language model. Okay? And we are trying to ask for features associated with the focus of the sentence. We are trying to find the best thing about the focus. Okay? So at this point, ChatGPT is going to come down into this cube. And this is a multi-dimensional cube. We saw how this has, GPT-3 had 12,800 dimensions or something like that. Hard to draw that. So I have a 3-dimensional cube, but just imagine that we had a 12,000 dimension matrix. And what it is going to do is going to figure out which feature it wants to select, because we are asking for the best feature here. Remember that. So it is going to go look for understandability. Is that the best part of the language model? It's going to look for maybe the ability to entertain you, maybe the ability to learn. These are all features. And it is going to go figure out which one makes sense the most using the same concept that we talked about. And it will then start generating text here like this. And every time it is generating new text, think of this in a multi-dimensional matrix, that it is reaching this point, then it is going here, it might go somewhere here, then it may go here, and it may go here. That's how it is generating this text right here. One other thing that I want to talk about this diagram before we move on, it is really important how you construct the prompt. And let me go ahead and erase all the markings on this diagram. So let me just go ahead and erase all of this. So let's clean up all of this. And the point I'm trying to make here is that the prompt that you start with right here, the prompt that you start with is really important because it determines where the model will start generating. So here you provided it the focus and you said, this is the feature you want. And in that 12,000 dimension matrix, it knows where to start. And the starting point is important because once you start, then it is going to start calculating the rest of the string. And this is why prompt engineering is so important, because the more you tell the model where to start, it's going to find the right location and it may be able to generate higher quality responses for you. It turns out that we need to understand one more concept before we can fully understand how ChatGPT is working under the covers. We've talked about large language models like GPT that generate text based on the probability. So they pick the word, then they generate the next word with the highest probability and the next word and so on. But it turns out that even though the generated text makes sense, it may not be preferred by a human user because all our preferences are different. And it would be impossible to create a loss function that captures my preference versus your preference. So it turns out that there is an additional technique on top of large language models known as reinforcement learning. And I'll talk about reinforcement learning in a second. But the important point here is it is reinforcement learning based on the human feedback. So before we go any further, let me just show you a very quick intuition for reinforcement learning. In fact, I have a YouTube video that I'm going to play just very quickly here. And this is a great example, my favorite example of just showing you how reinforcement learning works. And what we are trying to do here is we are trying to use this algorithm or a programming technique or a learning technique called reinforcement learning. So we are trying to park the car in this parking slot. And we have given it 4 or 5 things. We have given it the camera view, the rear view, the sensors, and we've given it a few things. And the goal here is for the car to park itself in the parking slot shown in the red. And every time it moves inside the slot, it gains, it is awarded some number. And every time it moves away from the parking slot, it does not get that reward. So the idea behind reinforcement learning is that you continue to change the parameters to maximize the reward. So as you can see here, this car is trying to learn to park. And of course, after 50,000 attempts, it knows how to park. But let me rewind the video when it is trying to learn to park. So here, attempt 5,000, it is trying to learn to park. It is trying to maximize all the values. And then it keeps doing that until the point it reaches where the reward function is maximum, which is somewhere here. Let's just play the video from here. And now it is able to come in and start parking. So we did not teach it anything else. We just said, here are the 5 sensors, modify the 5 sensors so you get the highest reward. That's in a nutshell. I provided you a very simple view of reinforcement learning, of course. Now let's go back to our whiteboard. So now that you know what is reinforcement learning, let's just go back to this diagram right here. So we start out with a prompt. We give it to the language model. The language model then generates some text. And this text is then seen by human users. So they have used, ChatGPT may have used something like a mechanical Turk to get a bunch of labelers to say which output do they prefer. So typically it will generate 2 outputs here for the same prompt. And the human labeler will then decide which prompt is good. And it is going to take that prompt and send it to this reinforcement learning. And we also take the prompt, the generated text, and then what the reinforcement learning is doing, and there's something called the proximal policy optimization that is going in and constantly learning. And once it learns this, then you're able to come up with a response that is preferred by humans. So this is a big innovation on top of the language models. And what was really interesting, that as these models have grown in size, what is really interesting is it is easy to train these language models by just a few prompts using this reinforcement learning approach, the proximal policy optimization approach. So hopefully this makes sense. So now you have an intuition for how ChatGPT is working. Let us go back to the slides for a moment. With this, we come to the end of this video. And then if you're interested, I'm going to be doing another video shortly where we talk about how these models are available to you within your subscription, within your Azure subscription, which means you can take that base model and then now you can fine tune it using data that you don't want to send outside of your network. So we'll be doing a video 2 series on that, and then maybe a video 3 series on some of the use cases. We begin to talk to customers about what kind of use cases. So I will motivate some examples that you may want to look at. Thank you again for watching.